Hello everyone and welcome back to this next video in the machines video simulation series, and this is where we had left off in the previous lecture where we had simplified the equivalent circuit of the single phase induction motor, and we had introduced the concept of referred parameters where we had taken all the rotor parameters and referred them to the stator, right? And this reference requires the turns ratio, and this is very similar concept with respect to transformers also. Even in transformers, you can refer the parameters of any winding to the other winding by using the turns ratio between the two windings, right? The advantage is now we have our entire single phase induction motor equivalent circuit as one complete circuit. This is not two separate circuits which are at two different frequencies. Rather, we have now merged them into a single circuit at a single frequency. It's important to note that this is for analytical purposes. Physically, nothing has changed. The induction motor is still what it is. It is a rotating machine. The stator is energized at 50 Hz, and the rotor has a frequency which is different from 50 Hz, which is multiplied by the slip. The reason? Because the rotor is rotating. It's a rotating machine as opposed to a transformer. So therefore, physically nothing has changed. But with all these simplifications, we now have an equivalent circuit with which we can work with. We can both analyze as well as simulate. So before I continue with this video, as usual, a little bit of brief background that if you're interested in these kind of video lecture series, but you would like something a little more comprehensive, I have full-length online courses which you can access on my website, which is pythonpowerelectronics.com. Basically the name of the project and .com. So this is the home page of the website, and in this you'll find these four buttons: download, learn, watch, read. And if you click on learn, it'll take you to this page with the courses. So these are my courses as of now. The very first course is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The next course is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and, more importantly, the signal package within SciPy to analyze and design filters specifically for power engineering applications. The third course is Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can simulate and model magnetic components like transformers, inductors and coupled inductors using Python and Python Power Electronics. The fourth course is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and specifically the Python control package to design and analyze controllers specifically for power electronic applications, and I do all my analysis with respect to the case of a single phase grid connected converter. And the very last course, the latest course I have, is a free course which is called Why Specialize in Power Electronics, and this is more of a motivational course targeted towards either junior undergraduate students or even high school students who are looking at which engineering domains they should specialize in. And the idea is to give you an overview of the opportunities and challenges which are available in the power electronics domain. So this is a completely free course, and the others are paid courses. So as you can see, all these courses are hosted on both the Decibel Labs as well as Udemy. So both of these are websites which contain courses, online courses that anyone can access. So if you want, go ahead and check it out on either of these two platforms. The link for this page is provided in the description for this video. So if you're interested, please do check out the description of this video. So with this, I can get back to my lecture. So as I said, this is where we had left off, and we now have this equivalent circuit. So now that we have this equivalent circuit, we can use it both for analysis as well as simulations. But in order to be able to use this, we need to know at least some of the parameters, right? Even if we don't have exact parameters, we should have some kind of an idea of how to estimate those parameters, or at least generate parameters which are close to what might be there in a practical machine, right? Now the only variable which is completely independent is this voltage source, because this is the source which you're going to apply. So for example, if this is a single phase induction motor, let's say for example if it's a simple pump or even let's say a ceiling fan, this would be energized at the power outlet which is available at any domestic power supply. And this would be either 240 volt 50 hertz, which is what we get here in Germany, or it could be anything such as 120 volt 60 hertz if you're in US or Canada. So if you want to know which voltage you should supply, just check out whatever is the voltage which is available at your domestic power outlet. Now about the rest of the parameters, these can, in practice, when you have an induction motor, there are two ways to do this. One is the manufacturer usually provides you some kind of data, right, based on certain amount of tests which are performed immediately after the machine has been fabricated. So you can refer to those. However, not always are these specifications available, and quite often you have machines which are bought second hand, third hand, or just bought out of auctions, and you don't usually have such documents, right? And documents started coming online only very recently. Some of the old motors, you still do not have any real specifications that you can find online. So the way to determine these parameters in practice is to perform a no-load test and a blocked rotor test, right? So in a no-load test, you would leave this machine in the unloaded state, right? So for example, what this means is, let me just write it down here. So for example, what is a no-load test? In a no-load test, the motor is not loaded, right? Which means that the only load on the motor is the motor itself, is the rotor itself. Because remember, the rotor also has a certain inertia, and therefore there is a certain minimum load that comes with the rotor, right? So, but other than this, we are not adding any separate load to the motor. So for example, if you're talking about a pump, this pump is not actually pumping any fluid, right? It is just running in the no-load state. Now, when this happens, all right, there are certain things you can make assumptions for. So for example, this slip, right, this slip, or you can say rather, the rotor speed is very close to the synchronous speed, right? This we've talked about before, and we've said we've even defined this slip as the difference between the synchronous speed and the rotor speed divided by the synchronous speed. So it's a kind of a ratio, which means that when this no-load test, when the motor is not loaded, the speed of the motor is going to be fairly high and very close to the synchronous speed. So what this means is this slip is close to 0 because it is NR is very close to NS. So therefore this numerator is almost 0. Right? Now typically it could be values like 0.01 or even lesser than that, or maybe 0.02, depends on the motor. Again, it all depends upon how much inertia the rotor itself has on its own. Now, because this slip S is so close to 0, if you take a look at this equivalent circuit, you will find that this S appears here on the equivalent rotor resistance, right? This RR dash by S. This equivalent resistance is now very large, alright, and because this equivalent resistance is very large, there will be a negligible current flowing in this rotor's part of the circuit, right? So now the question is, let me just write that down, RR dash divided by S is very large, and therefore the current which is drawn by this induction motor is mainly used in supplying the core losses of the induction motor, because the current is negligible. The only thing that the motor has to do is maintain its magnetic field in the air gap, and because there is a magnetic field, there will be some core losses, right? So these core losses will have to be supplied, and also there will be a current that is drawn, which is the magnetizing component of the current, because remember, we have a combination of a resistance and an inductance, right? These current drawn by these two paths will be 90-degree phase shifted with respect to each other. So there is a magnetizing component of the current and there is a core loss component of the current. These are the only two parts of the current which are drawn when the machine is at no load. Alright, these are the only two components. So what one can say is that because the current is so negligible, we can say that the drop across RS and LLS is actually negligible, right? Because this current drawn is just the bare minimum amount of current in order to maintain the magnetic flux and the core losses. And because this current is so low, you can almost assume as if this supply voltage is directly applied to this branch, the branch which is a parallel combination of RC and LM. So you could say that in no load, we can approximately say that the only current drawn by this machine is used for supplying the magnetizing current and the core loss component. That's it. So this assumption now helps us to find out what these two are. Now in a no load test, when you actually perform a no load test in the laboratory, you run the machine at no load for a certain amount of time, you let it stabilize, and once that happens, you measure the power. This power is the no load power, and this no load power is essentially the core loss component. And this core loss component, quite obviously, is VSRC raised to 2, the VSRC square divided by RC. So if in a laboratory we measure the no load power and equate this no load power, because we've said that at no load, the no load, or rather the only power drawn is for the core loss component, then in that case we can use whatever power is measured to estimate, to calculate this core loss component, RC. Again, important to understand, there is a certain amount of assumption made. We are assuming that this drop is negligible. We are assuming that the no load power drawn by the machine is 0. There is some amount of no load power, because remember, no rotor can have 0 weight. And because a rotor cannot have 0 weight, it cannot have 0 inertia, and therefore there will be some minimum torque or minimum load always with an induction motor. But we are assuming that is 0. Right? We are assuming that is 0. So therefore, we can use whatever power which is drawn by the motor at no load power to equate it to the core loss component. At the same time, we can also measure the current. Right? This is the no load current. And this no load current is now going into two different parts. Quite obviously, because whatever is the current, you can measure the current here. Typically, you cannot measure separately these two currents, because remember, this is an equivalent circuit. You can place an ammeter here, right? In the laboratory, we can place an ammeter here. So this ammeter will measure the total current drawn by these parallel paths, that is RC and LM. And we can now say that this no load current is equal to IM plus IC, where we are saying that IM is the magnetizing current and IC is the core loss component. Now we already have measured RC, which is equal to this core loss component divided by, we just have to plain arithmetic, take this RC to the other side, so it's VSRC squared divided by core loss component. So I is equal to IM plus VSRC divided by RC. Right? Actually, I should probably not put a dash here, but we put an equal to here. Yeah. So therefore, we are saying that this IC can be calculated from our previous calculation of RC. Now, and this again, assumption here is that the drop across this stator is negligible. Right? We can also calculate that, but this is the simplest way to do it. So now we can calculate what is this magnetizing component. And once you calculate the magnetizing component, we can calculate the value of Lm. Right? Lm is nothing but VSRC divided by omega into IC. Right? Because actually this, or rather, not IC, it is IM. Because remember, the magnetizing current is basically the voltage applied divided by the reactance of this magnetizing inductance. Right? So we're just doing a simple arithmetic. So if we perform a no load test on an induction motor, we can calculate the core loss component and we can calculate the magnetizing inductance with certain assumptions. We have made assumptions. We've assumed that this rotor circuit is completely open circuited because the slip is very small, and we have assumed that because the current drawn is so small, this drop across the stator resistance and leakage inductance is negligible. With these assumptions, which are actually quite reasonable, we can calculate the core loss resistance as well as the magnetizing inductance. This is the importance of the no-load test, and this no-load test is something that most of us as electrical engineers will perform in undergraduate studies when you're studying induction motors. I think I may have done this in third year. Usually it's done in either second year or third year, depending on which curriculum you follow. But usually the no-load test and the block rotor test, which I'll be talking about soon, is always there in the undergraduate curriculum. Alright. So, and these are also usually performed in many cases also in the laboratory when you have an induction motor. Because remember, even if you have manufacturer specifications are usually applicable to when the machine was fabricated. And induction motors are known to last for a long time, right? An induction motor can actually last for 20-25 years because especially a squirrel cage induction motor. So which means that if you are using a motor that's actually 10 years old, the parameters could have changed to a certain extent from when they was first fabricated. So if you have an old motor, you would still like to perform a no-load test and a block rotor test and try to estimate some of the parameters on your own rather than just relying on what the manufacturer has provided. Now, of course, in the simulation, we do not have a no-load test. So if I were to actually calculate this, I will assume certain core losses and I will assume a certain magnetizing current. Right? These are assumptions we make in order to estimate our parameters. But again, like I said, these assumptions are actually quite reasonable because usually most machines are fabricated to such kind of specifications. So this will come very soon, the next few lectures, when we start actually programming this induction motor model. So I'm going to stop now because the lecture's gotten already pretty long. But the idea was to tell you that this equivalent circuit that we have derived, we can now estimate these parameters either practically using no-load test and block rotor test, or in the simulation model, as we will see very soon, by estimating these parameters, not rather performing an actual experiment, but by estimating them using ballpark values which usually are expected from any motor. So, with this, I'm going to end this lecture. If you have any doubts about what I talked about, please do either comment or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will talk about the block rotor test and what parameters we can calculate using the block rotor test. So, thank you so much and see you soon. Goodbye for now.